In a 45-year-old patient of right-sided breast mass, USG examination revealed an equivocal appearance that was graded as BIRADS 3. A special application of an ultrasound technique was used, which is shown here, which is based on estimation of hardness of tissues. Identify the technique. Now, we are all used to seeing ultrasound images as extremely gray, dirty, blurred, black and white, grayscale images, right? But there are some specialized applications of ultrasound where color is used. One of them is color Doppler. We are going to see it. But also one of the recent applications is the use of ultrasound to, estimate the hardness or elasticity of the tissue. This is called as ultrasound based elastography. This is actually an elastogram image. We'll discuss this in some more detail as we discuss it. As we go ahead, this special method of ultrasound used for the eye, so this is the only application of this particular technique in the eye. This is called as the A scan or A mode. What is this A mode, B mode? Is there a C mode? And what is this M mode? There's no C mode, for your information. These are all methods of display of ultrasound data. How does ultrasound work, right? Now, these are all things that we are going to discuss when we go to the ultrasound animation here. Okay. So let us quickly discuss few historicals. So remember, it was Pierre Curie who actually discovered the property of piezoelectricity. So piezoelectricity, piezoelectric effect is the basis of ultrasound, and this was discovered by Pierre Curie. It was Carl Dusik who actually attempted USG imaging of the head for the first time. So he was the one who made an attempt of head imaging by using the technique of USG. Now it was, however, Ian Donald, remember, who used USG for the first time for obstetric imaging, and therefore he is the one who is called as the father of obstetric imaging, right? Ian Donald is called as the father of obstetric imaging, but it was John Wild, remember, who actually used ultrasound medically for imaging. So he is called as, he's given the designation of father of medical ultrasound. So father of obstetric ultrasound is Ian Donald, father of medical ultrasound is John Wild. Carl Dusik attempted ultrasound for the head imaging, and piezoelectricity was discovered by Pierre Curie. Now, what is an ultrasound beam? Ultrasound, if you remember, you must have studied it in physics in your 10th, 11th standard. It is nothing but a sound wave, right? So what is a sound wave? Sound wave, like an ultrasound beam, which is actually a sound wave, is a mechanical wave. It consists of alternate compressions, rarefactions. Compressions, rarefactions. Again, alternate compressions, rarefactions. During a compression, at the tissue site in the wave, at that particular site, there is an increase in the pressure. At the site of a rarefaction, there is going to be a decrease in the pressure. Now, what is a sound beam that we can listen to, and what is ultrasound and what is infrasonic? This all depends on one property of that particular wave, and that property is the frequency. So few frequencies I want you to know. In the sound spectrum, see, I have plotted the frequencies here on the y-axis. So if you just remember a frequency value of 20 Hertz to 20,000 Hertz, from 20 Hertz to 20,000 Hertz is the audible range of sound. This is something that we can listen to. We can't listen to something that is below it, above it. So what lies below, therefore, this is the sonic range or audible range. What lies below it is called as infrasonic. Less than 20 Hertz is infrasonic. 20 Hertz to 20,000 Hertz is audible range of sound or sonic range. And 20,000 Hertz and above, so above 20,000 Hertz is called ultrasound remember, the ultrasound part of the spectrum by definition is the one that lies above 20,000 hertz. Is the entire ultrasound spectrum used for diagnostic imaging? The answer is no. What is used for diagnostic imaging is the part that lies above 1 megahertz. So what is used in diagnostic imaging is the part above 1 megahertz. Quickly, MCQs can be asked. 20 hertz to 20,000 hertz is sonic range, audible range of sound. Anything below 20 hertz, infrasonic. Anything above 20,000 hertz, ultrasonic. Is the entire ultrasound spectrum used for diagnostic imaging? No. The part of the spectrum that lies above 1 megahertz is used for diagnostic imaging. Right? Now, let us look at the ultrasound machine. There are various parts of the ultrasound machine. This is nothing but the display monitor. Then there is a big console which is there, right? There are various probes which are attached, and ultimately we have the ultrasound gel. Why is the gel used? We'll discuss this when we discuss ultrasound image interpretation. At this point, let us discuss quickly what are the various probes which are used. It is this probe that the radiologist is going to hold and use for scanning. So various probes are used for different scan purposes, right? The probe with the least frequency, right? So least frequency probe is called as the pencil probe. It has a frequency of around 1 to 2 megahertz because it is like a pencil, like a pen, right? So it can be held in between the two fingers, very small probe. This is used for a technique which is called as transcranial Doppler or transcranial color duplex imaging. So TCD or TCCD or TCCS or scan. So it is used basically for transcranial Doppler or transcranial color duplex imaging. The most commonly used probe overall, right? So the most commonly used probe overall is called as the convex probe or curvilinear probe. Why? Because its surface that touches the patient's body is convex, like a sector like this. So this is a convex probe. This is the most commonly used probe, right? This probe has a frequency of around 3.5 to 5 megahertz. This is the probe which is routinely used for all the abdomen and pelvis ultrasound. This is the probe which is used for all the obstetric ultrasound. This is the probe which is used for the obstetric Doppler imaging. So if next time you go for an abdo-pelvis ultrasound, you see which probe the radiologist is going to hold. The radiologist is going to hold this particular convex probe. The next probe which is used is called linear probe because the surface of the probe is linear or flat like this. It has a slightly higher frequency, around 7.5 to 12 megahertz. And this probe is used for, just remember it this way, this is a small probe, linear probe. This is used for all the small part imaging. So it can be used for neck ultrasound, thyroid ultrasound, any small part, so eye ultrasound it is used, any swelling over the body anywhere of the local part, say the lipoma anywhere, right? This particular will be used. So for breast ultrasound, for almost all joint ultrasounds, right? This is used. This is also used for peripheral vascular Dopplers. This is also used for peripheral vascular Dopplers. Now, a linear probe, a tubular or a linear probe is called as a endoluminal probe. The shape is elongated like this, right? Frequency is high, more than 10 megahertz. And this is the probe which is also called as the endoluminal probe, endocavitatory probe. So this is used for the transvaginal ultrasound or sonography. So this is called TVS, transvaginal sonography, which is done for pelvic organs, early pregnancy evaluation, ectopic pregnancy evaluation. It is used for transrectal ultrasound. Transrectal ultrasound is used for evaluation of prostate. Transrectal ultrasound guided prostate biopsies can also be done. A similar thinner probe is used for transesophageal echocardiography, which is more sensitive for assessment of prosthetic valves, right? Endoscopic ultrasound can be done, a gastroscopy, duodenoscopy is done, ultrasound device is there, so pancreas head, pancreatic duct can be very well seen. So endoscopic ultrasound can be done, right? Endovascular ultrasound is also been devised now to assess the vessel wall. Right, so all the endoluminal probes have a very high frequency. They are very small probes, elongated probes. One of the probes which has the highest frequency, right? So lowest frequency we started with a TCD probe, pencil probe, do you remember? So highest frequency is what? It is called as a UBM probe. It has a frequency as high as 50 megahertz. What is this UBM? UBM stands for ultrasound biomicroscopy. It is used for what organ? It is used for evaluation of the eye. So UBM, ultrasound biomicroscopy of the eye. So highest frequency probe, UPM probe is used for this particular application, very rarely done, very specialized technique. Now if you look at the ultrasound probe, so this is the convex probe, right? Most commonly used probe, we have discussed this. What is there inside this probe? If you open up this probe, what you'll see inside is this. What is there? There is a wire attached to this probe. This probe will bring in the electric current, also carry away the signal. But at the tip, most important part of the probe are these piezoelectric crystals or piezoceramics. What is the basic principle of ultrasound? Piezoelectric effect, right? That is how ultrasound beam is produced. It is produced from what? It is produced from piezoelectric crystals or piezoceramics. There are multiple crystals on the surface of the probe. The most common crystal which is used is called as lead zirconate titanate. Lead zirconate titanate is the most commonly used crystal in our ultrasound machines today. Lead zirconate titanate is the most commonly used crystal in our ultrasound machines today. Now let us see how an ultrasound beam is actually produced. Look at this ultrasound probe here. Now this ultrasound probe has a wire which is attached to it. Now this wire brings in an electric current to the ultrasound probe. This electric current is passed through the lead zirconate crystals, lead zirconate titanate piezoelectric crystals. Now what happens when an electric current is passed through these piezoelectric crystals? Right, there is a realignment of the internal dipole structures of these crystals, as a result of which these crystals, they begin to vibrate. Can you see it there? So these crystals are vibrating now, but the frequency at which they are vibrating is more than 20,000 hertz. Just imagine if a crystal is vibrating at a frequency of more than 20,000 hertz, then it is going to set up mechanical waves around it. Because the crystal is vibrating at a frequency of more than 20,000 hertz, the mechanical waves are also going to have a frequency of more than 20,000 hertz. Can you tell me what are mechanical waves with a frequency more than 20,000 hertz called as? They are called as ultrasound. So see, what we have seen here is that when an electric current is passed through lead zirconate crystals, they vibrate and the result is production of an ultrasound beam, isn't it? Now the exact reverse of this also happens when an ultrasound is done. And what is that? See, so when an electric current is passed through a probe, through the crystals, they vibrate because of the realignment of internal dipole structures, and ultrasound beam is produced. This ultrasound beam is introduced into the patient's body, isn't it? Now what happens? It is reflected back from the patient's body, and when it comes back, just see, this is an ultrasound beam which is now coming and hitting the piezoelectric crystals in the probe. What happens when an ultrasound beam comes and hits a lead zirconate titanate crystal? Crystal deformation occurs, and the result is that an electric current is produced in the wire attached to it. This is exact reverse of what we saw before, isn't it? So what is happening here? Ultrasound beam, when it hits a lead zirconate crystal, there is crystal deformation, and the result is production of an electric current. So just see what has happened here. You know, this event that we've just discussed, that is an ultrasound beam, when it hits a lead zirconate crystal, gives rise to the generation of an electric current. This phenomenon is what is the basis of ultrasound, which is called as the piezoelectric effect. And the upper one that we studied right before, that is an electric current passed through a lead zirconate crystal, results in formation of ultrasound beam. This is called as the reverse or inverse piezoelectric effect. Right? Remember, when I say that piezoelectric effect is the basis of ultrasound, remember that both parts of this particular process, that is the piezoelectric effect and reverse piezoelectric effect, both of them are used in medical diagnostic ultrasound. Right? How are they used? What is the basic principle on which the image reconstruction occurs? Let us discuss this. This is what is called as the pulse and echo principle. Now remember that even before medical ultrasound was actually devised, the application of ultrasound in medical imaging was actually devised, this technique or this principle was being used by ships in a technique which is called as the sonar technique. What was this? Now just imagine that I have a cruise ship of my own. Oh, I wish I had a cruise ship of my own, right? And then I have sent the ship for conducting a scientific experiment. Who does? But let us imagine, for the sake of this example, I have sent my ship to conduct an experiment, and the experiment is that it is going to map the depth of the Indian Ocean. So I have sent this ship, right? It is sailing, and its function is to measure the depth of the ocean. Now, how did the sonar technique work? See, at the bottom of the ship, there is an emitter of sound. This emitter of sound is going to emit a pulse. Can you see this? The pulse is being emitted. This pulse is going to travel downwards, and it is going to hit the floor of the ocean. When it hits the floor of the ocean, it is going to get reflected back. An echo is formed now, isn't it? So a pulse is emitted, it gets reflected, and an echo is created. So because this principle is going to use a pulse and its echo, it is called as pulse echo principle. Yes. Now see, the time at which the pulse is emitted and the time at which the echo is received is measured by this ship. Now see, there is a simple formula that I know, and that is velocity is equal to distance upon time. Correct? So distance that I want to measure here, that is the depth of the ocean, will become equal to velocity of sound in water multiplied by the time required for it to travel. Now in between the emission of pulse and the reception of echo, do you realize that the sound beam has traveled the distance d 2 times? Once it is going in as a pulse and once it is coming up as an echo. So modifying this formula, if I just use half of this time, see, using a formula which is as simple as this, now I am able to calculate what is the depth of the ocean, isn't it? Right? So now using this same principle in human diagnostic ultrasound, see here, if I am trying to do an obstetric ultrasound, I keep a probe on the surface of the patient's body, right? When a reverse piezoelectric effect occurs, electric current is going to pass through the lead zirconate crystal, an ultrasound beam is produced. This will enter the body as a pulse. It will be reflected back by certain tissues, right? So that will be the echo. When this ultrasound beam hits the lead zirconate crystals, an electric current will be generated. That is the signal that is received. So using the same formula that we just used in the sonar technique, we will now be able to calculate at what depth this particular structure lies from the surface of the body, right? This is how ultrasound image is created. This is what is called as the pulse echo principle, the basic principle on which the ultrasound machine functions. Now I know I can measure the depth of a particular organ from the skin surface, but how do I create the ultrasound image, right? For that, we will now discuss what is called as the methods of display of ultrasound. There are 3 methods of display: A mode, B mode and M mode. What are these methods of display? Let us quickly have a look. So remember, A mode, the A in A mode stands for amplitude. What is this A mode? This A mode is a very primitive method or a crude method. Rather, it is a simple graph or a plot. What is this graph? Look at this graph. On the y-axis, you have amplitude. On the x-axis is the depth of origin of that particular signal. Right? Now see, when we do a pulse echo principle, I said that using the formula, we can calculate that depth that is plotted on the x-axis. But when the echo is received, the ship or the machine is going to measure what is the amplitude of that particular echo, and that amplitude is plotted on the y-axis. So this is just a graph of amplitude against depth of origin. Just imagine if I use this for say abdomen ultrasound, I will have multiple peaks because there are so many reflecting surfaces in the abdomen, right? In abdomen ultrasound, say I'll get a peak arising from liver, gallbladder, pancreas, right? I'll get it from kidneys, spleen, bowel, lymph nodes, blood vessels and whatnot. Is it possible for me to just to look at this graph and say, oh, this is liver, this is gallbladder, this is pancreas? No, Do you realize how crude, how primitive this method is? And therefore remember, A mode ultrasound is not used in human diagnostic imaging, except it is used for imaging of one particular organ in the body even today. And what is that? Anyone? It is used for ophthalmic ultrasound. In eye ultrasound, you have an A scan and a B scan, right? What is A scan? It is nothing but A mode of display. See, the ocular structure is very uniform. There are very few reflecting surfaces. What are those? Cornea, anterior capsule of lens, posterior capsule of lens, retina. That's it. So when I do a mode on the closed eyelid, a probe is kept. There are only 4 reflecting surfaces. They can very well be plotted. This is how a normal A mode ultrasound of the eye looks like, right? But now we want to actually use ultrasound in the other body tissues. This is done by using the most common method of display, which is called as B mode. What is B mode? B in B mode stands for brightness, remember. Now this B mode is actually just an extension of A mode. How is it an extension of A mode? See, in A mode, what do we measure? Amplitude, isn't it? And in B mode, when we construct a B mode image, this amplitude value which is measured in A mode is simply given a brightness value. Amplitude value is given a brightness value. How is it done? See here. So see, in B mode of display, just imagine if I am trying to scan this area of the patient's body, and ultrasound probe is kept, right? And pulse is, sent into the body and echo is received. Before we try to interpret this B mode image, look at that, left hand side of this particular image, you will see a gray scale. This gray scale is the basic of this B mode image. It is there in every B mode image. What do you see on this gray scale? There is the bottommost part of the gray scale, which is jet black. As you come up, there are increasing shades of brightness, and at the top you see it is bright white, right? Now what the machine does is that in this area of the patient's body, the machine is going to try and measure what is the amplitude value of returning echoes arising from each and every point in this particular patient's body. Now what will happen? See here, let us take up an example. Let us look at this point, or the points that lie in this particular area number 1. Now when you look at this area number 1, right, the machine found that the amplitude of returning echoes arising from these points in area number 1 was a very low amplitude. I said amplitude value is given a brightness value depending upon this gray scale. So low amplitude was plotted on the gray scale at its bottom because of its low numerical value, and therefore how does this area appear? It appears black or hypoechoic. Do you realize that? The amplitude value is given a brightness value. Now see, let us take another example. The points in the area number 2, the machine found had an intermediate amplitude. So where will this intermediate amplitude be plotted? It will be plotted at the middle part of the grayscale, and therefore these points appear gray or isoechoic. Now look at another example. The points in this area number 3, they were having a very high amplitude of returning echoes. High amplitude of returning echoes will be plotted where? It will be plotted on the top of the grayscale, so white. Therefore these areas, these points, they appear white or hyperechoic. So remember, the amplitude value of returning echoes at each and every point in this particular area is going to determine the brightness value of that particular point, and that is how a B mode image is created. Brightness mode, B mode image is direct extension of A mode image. Now what is this image? Can you identify? In this image you can clearly see the anterior abdominal wall, anterior uterine wall, right? The uterine cavity filled with amniotic fluid, and there is a fetus, the head of the fetus, the thorax of the fetus, the lower limbs of the fetus, isn't it? This is not a graph, this is an actual image of the patient's body, right? And therefore, because we are actually able to see those organs very well, this mode of display, B mode of display, is the most common method of display which is used. After A mode and B mode, the next method of display is not C mode, but it is called as M mode. What is M mode? M in M mode stands for motion. So what it is going to detect? It is going to detect motion. Look at this real-time graph there, right? On a B mode image, that line you see, along that line, the machine is going to see whether there is any motion which is occurring, and that motion is going to be plotted on this particular graph. This is just a graph of motion versus time. Because it detects motion, it is used to evaluate an organ which is constantly in a state of motion. That is the heart. So M mode is used in echocardiography, that is ultrasound evaluation of the heart. So this is about the methods of display, that is A mode, B mode and M mode, amplitude, brightness and motion. Now let us go to a specialized application of ultrasound, and that is what is called as Doppler ultrasound. It is based upon the Doppler effect, which was established by a scientist known as Doppler, and it states that, what is Doppler effect? It states that it is the change in frequency of sound that occurs whenever there is a relative motion between the emitter of sound and the receiver of sound. Did it make any sense? No? Let us quickly consider a simple example. Suppose that you've just finished your shift working in the hospital. You're just going towards your home. And when you're just at the hospital gate, you see an ambulance. That ambulance is coming rapidly towards the hospital. It is carrying an emergency patient. And the horn of the ambulance is, going on at a very loud volume. Now, when you're standing there stationary, right, the ambulance is moving, it is coming towards you. And you can listen to the horn of the ambulance, right? How will that sound, be like? Just try to listen to this particular sound. See? Yes? Did you see any difference in that particular sound? Now let us listen to it very carefully once again. See whether you can see that the pitch of the sound is changing. Listen to this sound. Just imagine the ambulance is coming towards you and then racing past you into the hospital. Listen to this sound. Yes? Did you realize that the pitch of the sound was actually changing? See what happens here. Look at this particular graph. When the ambulance is stationary, you are stationary. This is how the sound waves are coming out. They are uniformly spaced, constant wavelength. Now what happens? The ambulance starts moving towards you. So what happens? Look how the wavefronts at the front of the ambulance, they are pressed together. So the distance between the two waves is reduced. Wavelength is reduced. If wavelength is reduced, what will happen to frequency? Frequency is going to increase. So as the ambulance comes towards you, the frequency is changing. What is happening? It is increasing. So this is Doppler effect, change in frequency of sound whenever there is a relative motion between them. Right? Now what happens? The ambulance races past you. Right? Now look at the, what happens just behind the ambulance. The wave fronts or the waves are widely separated. So the wavelength has increased. If the wavelength has increased, the frequency is going to decrease, isn't it? So see what happens. When the ambulance comes towards you, right, you see a high frequency, or you hear a high frequency sound or a high pitch sound. Because the wavefronts are pressed together, wavelength as decreases, frequency increases, right? But when the ambulance is moving away from you, the wavelength has increased, so frequency decreases. You hear a low pitched sound. So the change in frequency of sound that occurs whenever there is a relative motion between the ambulance, that is emitter, and the receiver, that is you, this is what is called as Doppler effect. Now, how is this Doppler effect used for diagnostic imaging? Let us take up an example of abdomen ultrasound. See here. See, suppose this is the liver parenchyma here. Right, this is the portal vein, hepatic veins. You can see you are doing liver ultrasound. You keep a probe on the surface of the abdomen. The probe is stationary. Liver organ as a whole is stationary. So what will happen? A pulse is emitted, an echo is received. Is there any relative motion between them? Tell me. The probe is stationary, liver is stationary, isn't it? So there is no relative motion between them, isn't it? So will Doppler effect come into play? No, it will not. Right? So there will be no Doppler shift, no change in frequency of sound, isn't it? But what will happen if now I try to evaluate the portal vein? Look, if I am trying to evaluate the portal vein, inside the portal vein blood is flowing. Blood predominantly consists of RBCs. Each RBC is a reflector of ultrasound. All the RBCs are moving. So now when a pulse is emitted and an echo is received, there is relative motion between the ultrasound probe and the blood or the RBC which are moving. And therefore Doppler effect comes into play. Do you get the clue about the application of Doppler? Where is Doppler ultrasound used? Therefore Doppler ultrasound most important application is vascular imaging. Right? So it helps us detect the blood flow. It helps us to detect the direction of blood flow. It helps us detect the velocity of blood flow. And using this information, we can diagnose thrombosis, stenosis, flow alteration patterns, insufficiencies, right, on various Doppler studies. That is the beautiful application of Doppler. Before we go ahead to various types of Dopplers, let us quickly study what is called as the Doppler equation. So what is the Doppler equation? See, it stands for FD, that is Doppler shift, that is the change in frequency of sound, equals to 2 times F0, that is the transmitting frequency of the probe, which is constant, multiplied by V, that is velocity of blood flow within the vessel, this is a variable value, multiplied by cos theta, divided by C, C is the velocity of sound in human body, this is a constant value of 1540 meters per second. Now this theta that is used as cos theta in this equation, this is what is called as the Doppler angle. What is the Doppler angle? Look at the situation here. Doppler angle is nothing but the angle between the ultrasound beam which is emitted from the probe and the plane of blood flow. This is called as Doppler angle. Now how is the Doppler angle used in the Doppler equation? It is used as cos of its value, that is cos theta. Now look at one example. Suppose the blood is flowing in this particular direction and the probe is also angulated in this direction. So both of them are in the same plane. What is the angle between the ultrasound beam and plane of blood flow? It is 0. So theta is 0, cos of 0 is going to be 1. So this is the ideal value. But is it practically possible for us to angulate the ultrasound beam around the blood flow? It is no. See here, look at the carotid arteries. The carotid arteries are traveling vertically. The blood is traveling vertically. Can I angulate the probe vertically like this? It is very difficult. Therefore, this is not practically possible. What is practically possible almost every time is that the probe can be angulated slightly such that the value is kept somewhere close to 60 degrees. So, if theta is 60 degrees, that is the Doppler angle between the ultrasound beam and the plane of blood flow is 60 degrees, cos of theta becomes 0.5. Do you see in the numerator in the Doppler equation there is a 2 which is there, 0.5 multiplied by 2 will become 1, and therefore we must try and keep the Doppler angle always around 60 degrees. What will happen if the Doppler angle is 90 degrees? See here, that is the angle between the ultrasound beam and the plane of blood flow is 90 degrees, so cos of 90 is 0. Right, so the Doppler shift will be 0. Machine will falsely tell you that there is no blood flow. It is a fallacy or shortcoming of this particular technique, and therefore when you think of the Doppler angle, remember the Doppler angle ideally should be 0 degrees, but it is not possible. So practically it is kept around 60 degrees, right? And it should never be what? It should never be 90 degrees. Yes. Now let us come to the very fascinating application of Doppler, which is called as color Doppler. Look at this image here. Look at this video here. This is what is color Doppler. What is color Doppler? It is a subjective method of Doppler interpretation, which means that we can see the color flow on this image. Can we measure it? No. So it is subjective. Remember, the flow is given a color, either red or blue. Look at the gray scale. Just beside it, you can see a red and blue color scale. So red is above. So whatever flow is above towards the probe is shown as red. Whatever flow is below, it is shown as blue. Now remember, this red and blue direction is arbitrary. If I invert this scale, the colors are also inverted. They are not fixed. It is therefore subjective. The intensity of the red or intensity or brightness of blue is determined by the velocity of blood flow. Remember. Okay. So this color Doppler has one disadvantage, and that it has slightly low sensitivity, and therefore it can miss flow in certain situations if the flow is very slow. Therefore, there is an advancement of color Doppler which is called as power Doppler. What is the difference? This is also color coded information. This is also subjective method. We can see the flow, but we cannot measure the flow, right? But what is the most important difference? Can you see? It is a single color scale. There are no two colors, red or blue, right? So it is a single color scale, meaning that it does not give us a direction of blood flow. Towards or away, it cannot tell us. But its advantage is that it has very high sensitivity for detection of color flow. It has very high sensitivity, that is the advantage of power Doppler, but still it is subjective. I cannot measure the flow, isn't it? And therefore there is an objective method of Doppler interpretation that is called as a spectral Doppler. What is spectral Doppler? See, using the various formulae, the machine can actually plot a graph of frequency changes occurring against time. Using mathematical formulae, this frequency information can be converted to velocity information. So I get the velocity changes happening inside a blood vessel with time. Just look at this velocity against time graph. If you pick up the highest point, that is the highest velocity, it is called peak systolic velocity. Just look at the lowest point, that is called end diastolic velocity. If we calculate area under the curve, that will give us the blood flow volume to a particular organ. So now, using this graph, are you able to measure the blood flow? Yes. So therefore, this is called as objective method of Doppler. This is what is called as spectral Doppler. So this is a blood vessel with blood flow within it, and that is how the spectral Doppler tracing is obtained. This is what is the Doppler applications, that is color Doppler, power Doppler, and the objective method, that is spectral Doppler. Now, does ultrasound have any effects on the body? Yes, it has two types of effects. One is called thermal effects. What are thermal effects? See, ultrasound is what? Ultrasound beam is going to carry some amount of energy. That energy is going to get deposited into the body. When the ultrasound beam is blocked or attenuated, that energy will be deposited into the body, that will be converted into heat. So that is what is going to create the thermal effects, right? Now this is more in Doppler because more energy is used. It may produce tissue heating. So there is an index which is defined. How to measure this particular adverse effect? There is an index which is defined, which is called thermal index. What is this thermal index? So this thermal index is the ratio of power produced by the USG probe divided by the power required to increase the tissue temperature, by 1 degree Celsius. So power produced by your probe right now divided by power required to increase the tissue temperature by 1 degree Celsius. This is called as thermal index. Now remember that in order to increase the tissue temperature by 1 degree Celsius, if I want to increase the temperature of bone by 1 degree Celsius, I'll require different energy. To increase temperature of muscles by 1 degree Celsius, different energy will be required. So therefore, this thermal index has been defined separately as thermal index for soft tissue is different, thermal index for bone is different based on the different tissues. This is about the heat which is produced in the tissue. But do you remember I told you ultrasound is what? Ultrasound is a mechanical wave, compression, rarefaction, compression, rarefaction. This increased pressure in compression and decreased pressure in rarefaction can also create, certain effects on the body. These are called as mechanical effects or mechanical damage. This is more in organs that have multiple air-water interfaces, such as lungs, such as the bowel, right? So it is basically giving rise to damage of the tissue. When the tissue gets compressed during compression, suddenly, the pressure is released in rarefaction, the tissue can get damaged. This can give rise to mechanical damage. This is basically given a name. This is called as microcavitation. Remember this word. So there is an index which is defined, that is called as the mechanical index. The value of the mechanical index should always be less than 1.9. That is the upper limit which is used. Now, a special application of ultrasound is the use of ultrasound for measurement of hardness of the tissue, and it is called elastography. Now, it is most commonly used in breast imaging. It can be used in liver imaging or liver assessment, also liver cirrhosis, right? Now, we all know that a breast cyst may be pliable. Breast normal tissue is compressible. A breast cyst can also be pliable, right? But a breast cancer, remember, is known to be scarce. Scarce means what? It is known to be very, very hard. And if the tissue is hard, its elasticity will be low. So this elasticity, whether it is low, intermediate or high, is given a color scale, and this elasticity information is plotted on a color map. That is how, by determining the elasticity of the tissues, right, we are able to determine whether that tissue is soft, is it intermediate or is it hard. In breast, cancers are known to be very hard. That is a clue to the diagnosis. So in this question, when this image was shown, this ultrasound technique used based on the estimation of hardness of the tissue is what? It is elastography. This is a recent advancement as far as ultrasound is concerned. And we have discussed various methods of display of ultrasound. We have seen that what is used in the eye in the A scan is nothing but A mode, where we can see the cornea, anterior capsule of lens, posterior capsule of lens, retina. So what is this? This is nothing but the A mode of display.